All right, today we're going to be reviewing Lewis structures. Or not Lewis structures, rather electron configurations. So let's write out a couple electron configurations. Let's remember that the elements here are in the s block. This is where s orbitals occur. The elements here are in the p block. Helium is in the s block as well. These elements in the middle of the periodic table are in the d block, and these are the f block. And that's just where those types of orbitals live at. Okay, so let's do the electron configuration for helium. You always start at hydrogen, right? Hydrogen is on the first principal energy level, so that would be 1s1, and then you go to helium, you add another electron, that's 1s2. Let's do magnesium, right? We're going to start with hydrogen again, 1s1, go to helium, 1s2, then we go lithium, beryllium, that's 2s2. Remember, you can only fit 2 electrons in each orbital orientation. So it depends on how many orientations there are. We get to boron, that's 2p1. We keep going all the way to neon, that's 2p6. Then we go to sodium, that's 3s1, magnesium, 3s2. Right? S orbitals are spherical. P orbitals look like dumbbells. It can have 3 orientations. D orbitals have 5 orientations. And F orbitals have, 7 orientations. Right? So each one of those orientations can hold 2 electrons. So for example, S can hold 2 maximum, P can hold 6 maximum, as we showed here. D can hold 10 maximum, and F can hold 14. So let's do gallium, Ga. So, like I said, we start with hydrogen, 1s1, helium, 1s2, and we keep going. 2s2, 2p6, 3s2, 3p6. Right now we're at argon. So argon is right here. Right? So we keep going. Potassium, K, is 4s1, calcium's 4s2. But remember that when we start with the d orbitals, right, even though they occur on the 4th period, you actually start numbering them 1 period behind, right? So 3d10, that's gotten us to zinc here, and then gallium would be 4p1. So remember, anytime you start with the d, so d orbitals start at n-1, f orbitals start at n-2. Now what is this n? The n here is whatever your principal quantum energy level is, whatever your principal level, basically whatever row you're on. So S and P, they are exactly that. So if you're on the 4th row, the S and the P orbitals are 4s and 4p. But if you're on the 4th row, those d orbitals are going to be 4 minus 1, so it's going to be 3d. Once you get down to the 6th row, you'll see that we start with the f orbitals, which are going to be 4f, right? n-2, 6 minus 2 is 4. Once we go to 7, those would be 5f. So this is important. All right. Now let's talk about magnesium again. So I'm going to copy magnesium's electron configuration and put it right here. So what we're going to talk about now is core versus valence electrons. So valence electrons are those electrons at the highest principal energy levels. Right? That's basically what those are. Core electrons are those electrons at lower principal energy levels. So, if we look at magnesium, right, how many core electrons does magnesium have? Well, core electrons are going to be those electrons which are lower than the valence electrons. So our core electrons for magnesium are going to be here. Those include the 1s and the 2s and the 2p electrons, whereas the valence electrons are going to be those at the highest principal energy level. So it has 2, 4 plus 6 is 10, so 10 core electrons and 2 valence electrons. Let us do another example. So let's do chromium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Remember the d orbitals start one behind. So it's going to be 1, 2, 3, 4, 3d4. Now, I think it's probably easiest to figure out how many valence you have. So you look at the highest principal energy level. That would be 4s. Oh, let's keep our colors consistent, Mr. Hicks, please. Right? So these are going to be your valence electrons because they're at the highest principal energy level. That means that everything else is going to be core electrons. Core electrons. So we have 2, 4, 10, plus 8, 18, plus 4 is 22. So we have 22 core electrons and 2 valence electrons. Let's do another example. Let's do neon. 1s2, 2s2, 2p6. So again, maybe start by figuring out the number of valence electrons. It's all of those on the highest principal energy level, so the one with the biggest coefficient number. So here we have 8 valence electrons, and then everything else is going to be core. So this is 2 core electrons. Now, what's interesting, I think, is that in Lewis structures, the only electrons that are shown are valence electrons, not core. This is because core electrons generally do not participate in bonding. Right? In the same way that spectator ions didn't really participate in reactions, those core electrons aren't really going to be participating in the bonding. Valence electrons are the things in atoms that help them bond to other atoms. That's why Lewis structures pretty much only show valence electrons. All right, so now let me show you something that maybe will make your life a little easier. So we can do noble gas electron configurations. So the noble gases, helium, that's 1s2, neon, 1s2, 2s2, 2p6, and we'll do the next one, which is argon, 1s2, 2s2, 2p6, 3s2, 3p6. So basically what you can do here is that, say for example, we're doing the electron configuration for aluminum. So it would normally be 1s2, 2s2, 2p6, 3s2, 3p1, right? And that's not that hard to write out. But what do you notice? Notice that we have the 1s2, 2s2, 2p6 here, which exactly matches that for neon. So I can rewrite the electron configuration for aluminum as this. Right? What I did was I took the electron configuration for neon here and put it in brackets. And so what you're saying is that I have at least the electron configuration for neon plus the extra stuff that gives me aluminum. That's another shorthand way to write these out. So say, for example, I was doing carbon, right? Carbon's normal electron configuration is this. But notice that I have let's do some different colors. I have the helium block contained within, so I can rewrite this as helium 2s2, 2p2. In this example, it didn't really save much time, but think about if you were going to write something like for radon again. You could have just done xenon and then done 6s2, 4f14, 5d10, 6p6. Radon is on the 6th level, right? 1, 2, 3, 4, 5, 6. Yes. This, if you'll remember from that assignment, is much shorter than writing out everything up till xenon. So in the noble gas electron configurations, you're basically just taking the noble gas before your element and putting it down in front of it, right? Okay. I mean, it's true that radon is a noble gas itself, but I wanted to show sort of its valent electrons. Okay. Next thing. Ionic electron configurations. You're like, no ions, Mr. Hicks, I can't do it. That's okay. It's really nothing special. Say, for example, you have N3-. What does that mean? It is an anion, and it gained 3 electrons. So to write out its electron configuration, we'll do the same for nitrogen. So 1s2, 2s2, 2p3, right? This is for nitrogen. But we have N3-, which means that it gained 3 electrons. So I basically need to just add in 3 more electrons. So this would be 1s2, 2s2, 2p6, right? That would be the electron configuration for N3-. And the reason is because it gained 3 more electrons. Let's do another example. Let's do aluminum. No, let's not do that. Let's do calcium 2+. So this is a cation, and it lost how many electrons? 2 electrons. So to write out its electron configuration, we would think about calcium normally being 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Okay, but it lost 2 electrons, so calcium 2 plus is going to be 1s2, 2s2, 2p6, 3s2, 3p6. If you're thinking, well, how do you know which electrons to take out? You always take out your valence electrons. So start at the very top, the highest electrons, or the electrons on the highest principal energy level, and remove those. So always remove valence electrons at highest principal energy levels first. This is super important, right? You're always going to remove electrons from the highest principal energy levels first. And you're always going to add electrons at whatever the current highest is, in the case of an anion. Okay, final thing. We're going to talk about what it means to be isoelectronic. This is when two elements have the same electron configuration. You're like, well, how can that be possible, Mr. Hicks? Well, let's do a silly example. So we have hydrogen, 1s2. Helium, sorry. Hydrogen is not 1s2. Hydrogen is 1s1. Helium is 1s2. Right? But what would be the electron configuration for hydrogen minus 1? It would be 1s2. So these are isoelectronic to one another because you'll see they have the same electron configurations. Now, the only reason they have the same electron configurations is because this is an anion and it had to gain an electron. So let's do another example. So we have aluminum 3 plus is 1s2, 2s2, 2p6. Yep. The standard electron configuration for aluminum is 3s2, 3p1. So then aluminum 3 plus would be minus 3 electrons, so 1s2, 2s2, 2p6, and that's it. Okay? What is aluminum 3 plus isoelectronic to? You'll see if you look at the periodic table, if you count, it is isoelectronic to neon. 1s2, 2s2, 2p6 is the electron configuration for neon. So that would mean that these are isoelectronic. They have the exact same electron configuration, the same number of electrons as well. The reason that that's able to happen is because this aluminum had to lose 3 electrons. It is an ion, right? So if you're thinking about things that are isoelectronic, at least one of those has to be an ion, most likely. Let's do one more example. So we have fluorine, 1s2, 2s2, 2p5. We have the fluoride anion, so we added an electron. Right, let's notice that. What is an ion that is also isoelectronic? Or let's say, what is an ion of nitrogen that is isoelectronic to F minus, right? So let's think. Nitrogen is normally 1s2, 2s2, 2p3. So we want nitrogen's electron configuration to look like that of fluorine F minus. So how many electrons do we need to add so that they end up looking the same? Well, we're going to need to add 3 electrons. If you add 3 electrons to nitrogen, that's going to be nitrogen with a -3 charge. You added those electrons. It's more negative now. Now its electron configuration is going to match that of the fluorine, and they are going to be isoelectronic to one another. And that is everything today.